Hi guys, today I'm going to go over the electrophilic addition mechanism for AS chemistry for CIE. So starting off with electrophilic addition then, this reaction is mainly for alkenes and you have to know four main reactions for this then. So electrophilic addition, you need to know how to go from an alkene to an alkane. So the reagents and conditions for this would be nickel catalyst, hydrogen gas, and 140 degrees Celsius temperature. This reaction is also sometimes referred to hydrogenation or reduction. Next, you need to also know how to go from an alkene to a dihalogen alkane. So for this, you need to add the halogen in aqueous solution. So X2 for the halogen at room temperature. Commonly, we look at bromine water and it decolorizes in the presence of a C2C double bond in alkenes. Next, you also need to know how to form a halogen alkane. And this will be done using a hydrogen halide, so HX in the gaseous state at room temperature. And finally, you also need to know how to form an alcohol, and the reagents and conditions I normally tell my students to remember for this would be concentrated phosphoric acid catalyst, 330 degrees Celsius, and 6 megapascals. Another name for this reaction could also be hydration. But all four of these reactions undergo the electrophilic addition mechanism. So before I move on to the actual curly arrow mechanisms, I would like to go over some keywords that you need to use in organic chemistry. So whenever you're looking at a mechanism, you need to be able to identify the nucleophile. So if you remember, a nucleophile is normally a species which donates a lone pair of electrons, or normally a species that reacts with an electron deficient center in a molecule. So normally I remember a nucleophile as being electron rich. So this could start off your arrow as from being a lone pair, or you can have an electron rich bond, for example C2C double bonds in this case. Then you need to know what an electrophile is. So this is a species which accepts a lone pair of electrons. So normally this is your electron poor species. So normally whenever we've got a mechanism in organic chemistry, your arrows, curly arrows, always go, so this is the main rule, curly arrows always go from an electron rich to an electron poor area. Next, you have different types of bond fission. So whenever you're showing a curly arrow mechanisms, you're showing bonds breaking and bonds forming. So you've got the main type of bond fissions would be heterolytic bond fission. So this is when a covalent bond breaks and the two electrons in the covalent bond are unequally shared. So if you have a X2 hydrogen bond, there's a covalent bond here. So both of these electrons would be unequally shared when the bond breaks. So for example, like that, and you would end up with X having a lone pair of negative charge and hydrogen ions with a positive charge. Then homolytic bond fission is the opposite. So here what we have is you would have again the covalent bond, and this, when it breaks this time, the two electrons in the bond are shared between the two atoms. So this would break like this, and you would form radicals. Okay, normally homolytic bond fission only occurs for AS for your free radical substitution mechanism. So we're going to be focusing on heterolytic bond fission in this mechanism today. So then finally you have two types of arrows. You have double-headed arrows that look like this and single-headed arrows that look like this. So there's a difference actually in these two arrows. Double-headed arrow shows movement of two electrons, and a single-headed arrow shows movement of one electron. So again, single-headed arrow would be for free radical substitution. So today we're going to focus on only heterolytic bond fission, and we're going to be using double-headed arrows to show this mechanism. So looking at each mechanism in detail now, we're going to look at, first of all, the electrophilic addition of hydrogen to ethene. So if we draw ethene then, and we've got hydrogen added to this. So on its own, you need to understand first of all that the presence of this electron-rich C2C double bond, so the pi bond, actually repels the pair of electrons in the HH bond, and this negativity induces a polarity. So it induces a dipole on the HH. So first of all, you need to understand that the pi bond in the C2C double bond induces a dipole in hydrogen. So what you've got is the high electron density repels the pair of electrons in the HH bond, and this negativity induces a polarity. So based on this then, your nucleophilic center would be your C to C double bond. So that's your electron-rich area. So normally that would induce a positive dipole then on the H that's nearby, and therefore a negative dipole on the next hydrogen. So arrows go from electron-rich to electron-poor areas of the molecule. So in this case, your arrow needs to start in the middle of your C to C double bond. So arrow is going to go from the middle of the C to C double bond to the hydrogen that's electron poor in this case. So if you notice, we've got nucleophilic C to C double bond center, and then this over here would be your electrophile. So your arrow is going from the electron rich to an electron poor area. So now this is showing a formation of a bond between the C and the H. So now this H over here then has got two bonds. So that cannot occur because hydrogen can only bond once. So you need to show bond breaking of this H to H bond. So the arrow is going to go from the middle of the H to H bond to this other hydrogen over here. So this bond breaks using homolytic bond fission. So bond breaks by, sorry, I said homolytic, I meant heterolytic bond fission. Okay, so here your pair of electrons is unequally shared. So this hydrogen over here is going to accept that pair of electrons. So now we are going to form our intermediate. So an intermediate is normally a partially positive or negatively charged species that forms at a particular step of the reaction. These are normally stable enough to react with another substance, but not stable enough to be the actual final product. So in this case now, what we are going to form would be this intermediate. So because this molecule is symmetrical, it doesn't matter where we are adding the hydrogen. So you can put it on any carbon. And you end up with a positive charge there. So this now is called a carbocation, because it's got a carbon with a positive charge. And specifically, this would be a primary carbocation. So when I do another example, I'm going to look over the different types of carbocations we can have. Then the hydrogen from before then will exist with a lone pair and a negative charge. So now we've got a new electron-rich area, which would be this. So this would be your nucleophile. And the carbon with the positive charge, the carbocation, would be your electrophile in this case, the electron-poor area. So your arrow now goes starting from electron-rich area, which would be the lone pair, towards the electron-deficient carbon. So that's your arrow. And then finally, your product would be this. So you've gone from ethene to ethane in this reaction. Okay, so next then, let's do another alkene. So this time then, I'm going to take propene as your example. So this would be propene. And we are going to add then HBr to this. So same thing again, the C to C double bond induces a dipole on HBr. And this time it's going to be the hydrogen that has the delta positive and the Br has the delta negative. So your arrow goes from the middle of the double bond to the hydrogen. Hydrogen cannot bond twice, so you break this bond heterolytically. So now you have two options for the intermediate. So you could have the hydrogen going over here on this carbon. If I label the carbons 1, 2, and 3, you can have hydrogen going on carbon 1 or carbon 2. And this time each product does matter. So we've got then the first intermediate could be this one. Or your other intermediate could be this one. So what's the difference then? So you've got two different intermediates. The first one would be a secondary intermediate because the carbocation is surrounded by two carbons, and the following one would be a primary carbocation. So now we need to use Markovnikov's rule to figure out which one in this case is going to be our major and minor product. So Markovnikov's rule states that the hydrogen is added to the carbon with the most hydrogens, and the halide is added to the carbon with least hydrogens. And then finally, if we're looking at different carbocations, normally the more stable would be the tertiary. So if we have primary, secondary, and tertiary carbocations, primary is going to be the least stable, secondary is going to be more stable, and tertiary is going to be the most stable. So more stable. Carbocation intermediate. So looking at this then, why would a tertiary carbocation be more stable? So normally a tertiary carbocation is more stable, so therefore it will be the major product, gives major product. Because a more stable intermediate or carbocation is formed. This is normally because there's greater positive inductive effect from more alkyl groups stabilizing the positive charge. So in this case, from both of our intermediates that we've got, the more stable intermediate would be the first one, the secondary one. So this will give the major product, and this one will give the minor product. So both of these will be formed, but in different ratios. So looking at the next step now, so then we have Br minus with a lone pair, and same again, arrow goes from electron rich to electron poor area. Same down here, we'll have Br minus with a lone pair, arrow goes from the electron rich to the electron poor area. So your final compounds then will be, so we've gone from propene to our major product being 2-bromopropane, and our minor product being 1-bromopropane. Okay, so next then, let's have a look at the other two reactions then. So then I'll continue doing the following examples with just ethene then. So next we can add just bromine. So I can do this mechanism quite quickly. So same thing again, electron-rich C to C double bond induces a dipole on the Br. Arrow goes from the middle of the double bond to the Br. This Br cannot form two bonds, so this bond breaks heterolytically. In the exam, you must show curly arrows properly and any relevant dipoles, charges, and lone pairs. So it is very important you put these in the right positions. Next, our intermediate then will be the carbocation. So since we're adding a diatomic molecule again, it doesn't matter where our carbocation goes in this case, because it's a symmetrical molecule. Oops, that should be Br. And you'll have a carbocation there. And the other bromine with the lone pair then attacks that electron pore area, and you're going to form your product. So you've gone from ethene to 1,2-dibromoethane. And finally, let's look at how the alcohol is made. So I'll stick to simply ethene again. So this time you've got water, H2O. So again, the C to C double bond induces a dipole on this OH bond. So you're going to have delta positive there, delta negative there. So the arrow goes from the middle of the C to C double bond again. And this O to H bond has to break. So now here, be careful, you need to show breaking of the OH bond from the middle, and the electrons is gone to the oxygen then. So once again, you're forming an intermediate. Doesn't matter where your carbocation is because your molecule's symmetrical. And then you're left with OH minus. So now be careful, the OH, the minus belongs to the O, and the lone pair is also on the O. Some people tend to put the minus on the H, but that's not correct technically. So now your arrow goes from the lone pair to the carbon. And then if you have to draw the displayed formula for this, you should be drawing the O to H bond as well, or you will lose marks. So you've gone from ethene to ethanol. Thank you very much for listening. I hope this was helpful, and I'm planning on doing more videos on organic mechanisms soon. Thank you guys. Bye.